Continuity, one of my favorite topics in AP Calc, and we get started right here in section 2.3 when we explore continuity. In terms of the AP exam, the topics that we are going to look at are 10, exploring types of discontinuities. There's your understanding, objective, and knowledge. Defining continuity at a specified point, understanding, objective, and knowledge. And I think we got one more here. Topic 1.12, which is confirming continuity over an interval. Remember to take good notes. Remember to hit pause. I'm going to go through this kind of quickly. So make sure you are bringing your questions tomorrow in class and keep up with those worksheets. Uh-oh, I look forward. I got one more. Removing discontinuities. Topic 113. Those are all of the AP topics we are looking today. And then we'll get started with this bad boy right here. Take some good notes and do those worksheets. Okay, so here we go. Here goes. When dealing with continuity, we kind of have a really basic definition, and it's kind of this guy right here. Not allowed to really ever say this, but it really helps us to understand the idea of continuity and what's going on. It's, can you draw the function without ever lifting your pencil? And if you can, then we say that, hey, that function is continuous. Now remember, this is not a definition you should use after today. All right, so let's go ahead and introduce ourselves. And the best way to introduce ourselves to continuity is we look at discontinuities, okay? And we have two main types that we deal with in AP Calc and functions that we are going to be looking at. One of them is a removable discontinuity. If you notice when I drew this, I had to pick up my pencil to draw it, or my pen, my red pen. Now, regardless, you know, you could have a parabola, maybe there's a discontinuity right there. We call that removable, okay, AKA a hole. But that's a removable discontinuity. Why is it removable? Because when we're working on problems, which are usually rational functions, we remove it. And it actually looks like it's part of the graph, especially if you type those types of functions into your sweet TI-84 calculator. Now, what's a non-removable look like? What can I not fix? Well, when we deal with piecewise functions, this comes up sometimes. Okay, and you get maybe a piecewise function that looks like that. Okay, this is what we call a jump discontinuity, but it's non-removable. Can't fix that. Okay, problems like these removables we could actually fix and maybe fill in that hole. You'll see it's a big part of what we do here in section 2.3. Our next one is, hey, sometimes we deal with vertical asymptotes. Okay, and when we deal with vertical asymptotes, we say that infinite discontinuities. And an infinite discontinuity would go in that non-removable case. Okay, to get further understanding of what's going on here in terms of continuity and discontinuities, let's look at this nice little picture over here. And let's go ahead and describe when it would be continuous in interval notation. So this problem right here, this graph would be continuous on the intervals from 0 to 1, union from 1 to 2, union from 2 to, it's colored in there at 3. So we say from 2 to 4, union from 4 to, is that a 6? I think it's a 6. From 4 to 6. I think it's supposed to be a 5, isn't it? Maybe I'm just getting older, but I'm going to call that a 5. Because it looks like it goes by increments of 1. Now, if you notice, I started with a bracket, I closed with a parentheses, because depending on what calculus book you look, sometimes we include endpoints, sometimes we don't. We will do what your textbook does, so we'll put brackets when it's at the end, as long as it's closed in there, and it does look like it's closed in there. Now, what about, where would this be discontinuous? And it would be discontinuous, sorry guys, it'd be discontinuous at x equals 1. And sometimes we want to describe what kind of discontinuity that would be. That would be a removable discontinuity, okay? What else do we have here? Ooh, at x equals 2, that's a discontinuity. X equals 2, remember, that's called an infinite discontinuity or a non-removable non-removable discontinuity. And then my last one is I have a discontinuity at 4. So we say x equals 4, and that again that's a jump discontinuity, which we also call a non-removable discontinuity. Okay, so hopefully that gives you a little bit of understanding of what's going on. Okay, here we go. Let's do B. I really hope you tried it on your own here. Now we're going to do this at C equals 4. So we're going to look right there, okay, you guys? So let's do the limit as x approaches 4 from the left of our graph up there. Is that equal to the limit as x approaches 4 from the right of the graph up there? And you know what? Do all of those things equal the function value at 4? So let's go ahead and look at this bad boy. As we approach 4 from excuse me, from the left-hand side, it's this green piece. And if you look there, it goes to a height of 3. Okay, is that equal to the value as we approach from the right? Oh, snap. That looks like it goes to 2. So those are not equal. So already there's no way that this guy could be continuous. Why? Well, we saw earlier that that's a non-removable discontinuity, and that's why it failed right there. It does not matter that when you find the function value at 4, that dude's colored in right there, it's equal to 2. So who cares that those guys are equal to each other? What we would say in terms of a statement for this would be, let's use this fancy therefore symbol this time. Therefore, right? Mathematicians are lazy. So we try to find symbols to save us some work. Therefore, f of x is not continuous at c equals 4 because the limit as x approaches 4 from the left-hand side does not equal the limit as x approaches 4 from the right-hand side. And since the limits aren't equal to each other, that would represent a non-removable discontinuity. And if there's a non-removable discontinuity, there's no way that we could be continuous at that point. You know what? Take a real quick look at this picture here. And if we look at 3, that dude's continuous there. Remember that easy definition for this guy? If you don't have to pick up your pencil, it means it's continuous. So if you were wondering what's an example of something being continuous, at x equals 3, that would be continuous. Okay? Okay, so we don't always get a picture. So you're going to have to do some of this stuff algebraically as well. So let's look at example 3 right here. Okay, you guys? Example 3, determine whether g of x equals 2x squared minus x plus 6 is continuous at x equals 2. Justify your answer. If g of x is not continuous, extend the function so that it is continuous. All right, so here we go. This is one of my favorite problems. Well, for one, why are we looking at x equals 2? Well, hopefully you notice that the domain for this particular function would be all real numbers, except when x is equal to 2. Now, why would that be? Well, because I get 2 in the denominator. And whenever I get 2 in the denominator, that means it would be undefined. Okay, so looking at that being my domain, what can we talk about in terms of this particular function? Well, if we look at this bad boy, one way to get this guy started in dealing with continuity, if we want to see if it's continuous at x is equal to 2, is we're going to go ahead and write down the definition of continuity. So whenever you see that, that's what you want to do. Now, the definition of continuity, remember, is the limit as x approaches 2 from the left-hand side, this time of g of x. Is that equal to the limit as x approaches 2 from the right-hand side of g of x? And is that equal to the function value at x is equal? Okay, so let's do a little bit of side work right here, right? Because in able to go ahead and use that definition continuity, I'm going to have to find out what the limit is as x approaches 2 from the left-hand side. And in able to do that, what I'm going to have to do is I'm going to have to simplify a little bit. Well, shame on me. First step is what, class? First step is to use my original function and use direct sub. Now, when I use direct sub, whether it be from the left or the right-hand side, I get 0 over 0. And what do we do, class? If we get 0 over 0, we do something else. Okay, now what does this guy look like? This looks like I'm going to And I'm going to put a little plus or minus because believe it or not, I'm going to get the same value for this one, okay? But I'm going to go ahead and factor that bad boy on the top. And if I factor that, I get 2x plus 3 times the quantity x minus 2. If you're not good with factoring, come on in and I will help you guys out with it, okay? Now, if you notice, you plug in a 2 right now, you still get 0 over 0, but bang, bang, choo-choo train, we get rid of those guys right there. And so I'm going to go ahead and write this. Now, why does it not matter from the left or right? Well, because you know why? I don't have a piecewise function. And if I don't have a piecewise function, the left and the right are going to be the same thing. So if I plug a 2 in right now, I get an answer of 2 times 2 plus 3 would be 4 plus 3, which would be 7. Okay, what the heck does that mean? That means I have a removable discontinuity, aka hole, at 2, 7. So let's do a little note here. Hole at 2, 7. Okay? And that's a removable discontinuity right there. Okay? Now, if you notice for this particular problem, your function value at g equal 2 would actually be undefined, right? I got a 0 over 0 for that. So if I wanted to start filling this guy out, the limit of that is equal to 7. The limit of this is equal to 7. And if you remember to the example that we did previously, whenever that does occur, we get a removable discontinuity if our function value is something else, which in this case is DNE. So guess what? We would say that g of x is not continuous. Therefore, fancy little therefore, g of x is not continuous at x equals 2 because the limit as x approaches 2, remember, I don't have to do left or right because it's actually the same thing, of g of x does not equal g of 2. Now, the cool thing about this problem is that they say justify your answer. That's all my justification right there. That's what that therefore symbol does. And it says if g of x is not continuous, which it is not at x equals 2, can you extend a function? Now, boom, I'm going to use blue because this problem gets even more cool right now. I'm going to cheat. Okay, I'm going to cheat a little bit. And what I'm going to do is I am going to create a new g of x so that this dude works out. Now, in able to do this correctly, guess what? I have to create a piecewise function. Okay, now I do want you to know before we get to this piecewise function what's going on a little bit here, okay? And what's going on is if you were to graph this in your calculator, this crazy function right there, looks like a crazy hard graph, actually is going to look like that. It's going to look like a line that has a y-intercept at 3 and you go up 2 over 1, it's going to look like that. But guess what's going to happen at 2, 7, 1, 2, up here at 7? If you look at your graph, you're not going to have a value there. Why? Because it doesn't exist. That's a removable discontinuity. So what we're going to do now is we're going to create this brand new dude, make this fancy little brace, and we're going to say, hey, let's use our original problem, which is 2x squared minus x plus 6 over x minus 2. And let's use that piece when x is not 2. Because when x is not 2, we're good to go. I mean, look up here. We got that graph is good to go everywhere when x is not 2. But when x is 2, we want to use something else. Class, what do we want to use? We want to use that guy right there, 2x plus 3. And what it's telling this graph to do is it's telling us to draw this. And you're going to say, well, isn't that the same thing? Yes, it is. But this second bottom piece says when x is equal to 2, fill that in. Guess what? Now I have a continuous function at x equals 2. I don't know about you, but that is pretty darn cool. Example 4. One thing that helps us out when dealing with continuity and whether or not a particular function is continuous or not is looking at a function's domain. So here we get something interesting happen. Let's go ahead and look at some domains, okay? Because this one here does not ask to specify at a specific point whether it's continuous or not. So we kind of look at the domain, we look at things that aren't at the domain, we look at the set of all real numbers. And we use the definition of continuity to help us to figure some things out. Well, hopefully when we all look at that particular rational function, we all notice that there's no way x could be 1. If x equals 1, I would get 0 under, which means it would be undefined. So this particular domain would be negative infinity to 1 union 1 to infinity. And I don't know about you, but if I take 1 out of the equation, if I take that 1 out of the equation, everything's okay. Everything's okay. So that means it's going to be continuous everywhere else, but it's not going to be at 1. But you know what's interesting about this right here is that if we were to use the definition of continuity and we were to inspect it at 1 from the left-hand side of f of x, and I were to inspect it as we approach 1 from the right-hand side of f of x, and I were to look at the function value. Well, 1, this is kind of easy to know why it doesn't exist, and that's boom, right there, right? It doesn't. But what's interesting, and one thing I want you guys to notice about this is hopefully you knew that there was a vertical asymptote at x equals 1, which means the limit as we approach 1 will be dne, because it will grow without bound. The limit right here will be dne. It will grow without bound. Now, don't do some crazy dne means it's good to go. No way, Jose. Okay, that fails like on every way imaginable. So that's A. Let's go ahead and look at B. B makes us think a little bit more. So that's the problem that is definitely a lot more fun to do. And it's a piecewise. H of x equals. You know what's interesting about this bad boy is if I look at that top, hopefully you know that's a graph of a line. Guess what? A line is always continuous. Always. Okay, boom. That bad boy is a parabola. A parabola is always continuous. So what could be the problem here? Well, it's a piecewise function. So you know what's cool about this guy is you get sometimes a line and you get a parabola that looks like that. Okay, is that guy continuous? Not there. There is a jump. Whoops, there's a jump right there. So what this question is kind of asking is that x equals 1, that line and that parabola, do they connect? And if they do, guess what? That bad boy is continuous. So what can help me to figure out if this piecewise function actually looks like this, where you might have a jump and not continuous, or like that? And the thing is right, the line's continuous everywhere, the parabola is continuous everywhere, so the only thing that can maybe mess it up is that x equals 1. So what are we going to use? Use the definition of continuity, which is the limit as x approaches 1. From the left to piecewise, the left and the right are definitely two different things. And guess what? When they are, I'm going to actually write this out just so that I don't make any mistakes with what I'm dealing with. Right? If I'm coming from the left, I'm going to use that top, right? Because it is less than 1. And then I'm going to inspect the limit as x approaches 1 from the right-hand side of x squared. Why x? Because boom, bang. Right? We're going to use that when it's greater than. And then what the heck am I going to use when for the function value? All right, so let's check out this bad boy. Now, how do we do limits? First up, direct sub that bad boy. Let's direct sub. So I get -2 times 1 plus 3. Let's do some math there. Ooh, I got 1 as my answer. Okay, so let's see if these guys meet up. And that's what this step right now is doing. Does the line meet up beautifully with the parabola? Now, first step, direct sub. 1 squared. What's 1 squared? 1. Sweet. Those guys match up. And then what about the actual function value? Well, which piece am I going to use? Oh, is it that simple, Mr. Tanaka? I just got to look for the equal sign. So let's use that bottom piece. It's 1 squared. That is equal to 1. Oh, snap. 1, 1, 1. Very cool. It's going to look like that, boy. So what do we do? Therefore, h of x is continuous at x equals 1. Why? Because the limit as we approach 1 of h of x. Now, believe it or not, I can just write this. I don't have to do a left or a right. Why? Because they're the same thing. And if they're the same thing, then that means I can just write it as x approaches 1 is equal to the function value. Boom. And that is the most important thing. That defines continuity. Now, yes, some people are saying, Mr. Tanaka, you drew it with a positive slope. If I really wanted to draw this, right, it'd be like that. It'd be down 2 over 1. So it'd look like there. Shame on me, because right at 1, it would be an open circle for the line, right, class? And And since it's an open, and then what I would do is, I would fill it in and then draw a parabola or the rest of the parabola. Okay, but it might be important to go ahead and go off to the side. See if you can do a little bit better job than I did of graphing that. But it's cool how it's totally connected, which makes it totally continuous. Oh my gosh, sweet. Check out example 5. That dude's got 3 pieces. I don't think it could get more fun than that. 3 pieces, and they're asking me continuity? Whew, that's a parabola. That dude's continuous everywhere. That guy's an exponential. That dude's continuous everywhere. That dude's a line. That dude's continuous everywhere. Oh, and then they're throwing in some A, dude. So I got to find some value of A that will make it continuous. Well, boom, right when I see that word, what do I do, class? Yes, yes. Definition of continuity. And where could this thing fall? Well, if that's continuous, that continuous, it could only fail at x equals 1, right? It could jump. It could jump. So let's go ahead and inspect this guy as we approach 1 from the left-hand side. Now, left-hand side, what am I going to do? Sometimes the AP will be tricky. I'm going to use the top one. Is it always the top one? No, the left side would always be less than that value. Okay, so it'd be x squared plus 7 equals the limit. It's got to be equal to each other, right, to be continuous. And the problem here is we're going to find A to make this guy continuous. Okay, it's going to be interesting, the one that works out. But this is like the fun one. Okay, 3x minus A. And that has to equal to the function value. The function value. So we'll just write g of 1 here. Okay, but what am I going to use g of 1? Hopefully you're like, oh, shoot. You're not going to use either the top or the bottom. You're going to use the middle guy. That's what I'm talking about. I don't think it could get more fun. All right, let's evaluate these limits. What's my first step? Direct sub. Let's take that 1 and let's plug that in there. What do we get? We get 1 squared plus 7. That gives me 8. Okay, let's plug a 1 into the next guy. What's happening here? I get 3 times 1 minus A, right? And so I get 8 equals 3 minus A. Well, that's a little strange. Okay, I can deal with that. Equals, what do I do for the g of 1? Well, I'm going to use the middle one, and I'm going to put a 1 wherever an x is, and then I'm going to use my math skills. Oh, that's 6e to the 0 plus 2. Ooh, what is e to the 0? Well, that's 1. So I'm going to get 6 times 1 plus 2, which is 8. Oh, snap, that equals that. That's a good thing, right? Because I need all 3 of these things to match up. Well, now I'm going to go ahead and work with 8 equals 3a. Now, why am I going to work with that? Well, 8 is equal to 8, so I don't have to use that last piece. And guess what? That's going to enable me to find out what a is. Do a little math here. I get a 5 equals a negative 8. A is equal to negative 5. So guess what that means? If I plug a negative 5 into this right here, I get 8 equals 8. Excuse me. And what does that mean, class, if all 3 of those are equal to each other? That means that we are dealing with a piecewise function that is continuous everywhere. Now I'm going to erase this stuff. Boom. Because I got to write a statement now, right? We always write a statement. Therefore, when a is equal to negative 5, g of x is continuous for all real numbers, because the limit as x approaches 1 of g of x is equal to g of 1. And when does that happen? When a is equal to negative 5. I told you that would be fun. We have 3 really, really important theorems in AP Calculus. So we attack the first one right now. And I already have the notes written out for you so I can really explain what's going on. What I would really ideally like you to do is just listen and then write down later, okay? But I have them all done right here, okay? So let's go ahead and talk about these guys. The intermediate value theorem. It's a direct application of what continuity talks about. Okay, in order to use any of our theorems, there is always going to be a very important hypothesis which must be satisfied. That's our hypothesis right there, which means if we have f being a function, f being continuous, and f being on a closed interval from a to b, then there will be at least one value of c that is in between a and b such that f of c is equal to k. Okay, now this is always really tough for a lot of our students to understand. So the intermediate value theorem tells you that there must be one c that exists, but it does not give you a method for finding c. This theorem is an example of an existence theorem. It's just saying that it happens. Okay, example 6, in the intermediate value theorem, what are the necessary requirements in order to apply this theorem? Okay, it's got to pass all of this. Okay, it's got to pass the vertical line test, making it a function. It's got to be continuous, and it has to be on a closed interval. Okay, and what's important to notice, go ahead and look at my picture. Okay, and if we want to go back to our original definition of what C and what K are, okay, K is on the y-axis. Okay, important to note. Okay, it's a y value. Okay, C is an x value, which is on the x-axis. So let's say we have that closed interval from A to B right there. Okay, and we're saying that C is in between those two, right? It's all right there. C's got to be somewhere there. Okay, as long as we're on a closed interval, it's a function, which means it passes the vertical line test, and it's continuous. Okay, you have your f of b right there. You have your, you have your f of a right there. You have your f of b there. It is saying that if I take any c, there's going to be somewhere where every value is hit in between those two guys, right? And if you notice, every value is going to be hit. And every value is going to be hit because it passes a vertical line test. It's continuous, and it's on a closed interval. Example 7, let's take it even a step further here, and I'm going to work through with you on this one. Okay, example 7, consider the function. Okay, we have a picture right there. Question 1, is f continuous on A to B? Yes, it is, because I can draw that entire graph without lifting my pencil. Okay, is k between f of A and f of B? Yes, it is. It is right there. Okay, in this example, if C is in between A and B, then there are how many C's such that they equal K? Well, guess what? Where are my C's between A and B that if I go up here, it equals that value of K? So there you go. There's one of them. Let's call it C1. Do I have any more? And the way you can find it, now if you notice, this is boxed in here, right? Because it's from A to B, that's where it's continuous and on a closed interval, and it's a function, and it hits one time, two times. Let's call that guy C2. And does it hit again? Oh, snap. This dude hits 3 times. The intermediate value just says it's got to hit one time. And it's got to hit one time as long as it's a vertical line test. It's a function. It's continuous, and it is a closed interval. So there you go. I kind of answered all of those questions all in one. A lot of these are just interpretation problems. You just need to know it. When we do AP Calc questions, free response, you'll have a better understanding of what's going on. Sometimes we might have to deal with it algebraically, and we're going to do that right now with example 8. Now, the AP makes us write a real fancy statement whenever we're dealing with anything surrounding any of these theorems. So here we go. What would I write on the AP? Since f of x is continuous on the closed interval 2.5 to 4, and f of 5 halves is less than 6, right? It was 5 and 5/6, and f of 4 was equal to, oh, I'm sorry, not equal to, we'll just go as greater than 6. The IVT guarantees an x value, C. And guess what? That x value is going to be between 5/2 and 4, such that f of that C value has to equal 6. Now, anything in your practice that deals with the IVT, get good at writing that statement. You'll thank me at the end of the year. Sorry, class, that's the first one that's just over 30, so I'm going to give you a little bonus. I got my little Rubik's Cube right here that I'm getting pretty good at. Anybody that could prove to me that you could beat me with this bad boy tomorrow before school starts, I'm going to help you out. Aloha.